For years, the artificial intelligence race was measured in chips, model sizes, and data centers. Now the competition is moving into factories, where software is receiving arms, legs, cameras, and hands. China isn't merely building humanoid prototypes for exhibitions. It's trying to turn them into a new industrial workforce, produced in volumes large enough to change the economics of manufacturing. That shift is already visible in the shipment numbers. Officially reported industry data says Chinese companies shipped roughly 14,400 humanoid robots in 2025, equal to about 84.7% of the global market. That's not the same as saying robots have replaced most human workers, but it does show where the first large production base is forming and why manufacturers everywhere are watching China so closely. Only a few years ago, humanoid robots were costly research machines that struggled to cross a smooth laboratory floor. Today, Chinese models carry bins, sort components, inspect products, move materials, and train inside real production environments. Most remain limited and many deployments are pilots, yet the direction has changed. The question is no longer whether these machines can move, but whether they create value. This matters because factories don't buy science fiction, they buy predictable output. A robot can perform a backflip and still be useless on an assembly line if it can't repeat a simple task for 8 hours without dropping a part. China is now closing the gap between demonstration and deployment, turning spectacular machines into dependable equipment that can be ordered, serviced, and assigned to a shift. The pressure behind this transition isn't difficult to understand. China became the world's manufacturing center through scale, infrastructure, and a vast labor force. But the demographic conditions that supported that rise are changing. The population is aging, the number of young workers is tightening, and fewer people want repetitive factory jobs that involve night shifts, heavy lifting, heat, noise, or long hours beside moving machinery. Meanwhile, wages and employment standards have risen as the economy developed. That's positive for workers, but it changes the calculation for manufacturers operating on thin margins. Companies must balance higher labor costs, complex products, shorter schedules, and competition from lower-cost regions. Automation is no longer only a technological ambition. It is becoming a practical response to labor scarcity and production pressure. Beijing treats robotics and embodied intelligence as strategic industries, not isolated research projects. National plans, provincial programs, universities, local funds, and industrial parks are moving in the same direction. The goal is broader than producing one famous robot brand. China wants the motors, sensors, batteries, control systems, data, software, factories, and standards required for a complete robotics economy. That ecosystem rests on an unusually large automation base. According to the International Federation of Robotics, China had over 2 million industrial robots operating in 2024 and installed about 295,000 new units that year. Those figures refer mainly to conventional industrial robots, not humanoids. But they reveal something important. Chinese factories already know how to buy, integrate, maintain, and improve machines at enormous scale. Humanoids can build on that experience instead of starting from zero. A factory already using machine vision, mobile platforms, robotic arms, digital production systems, and predictive maintenance has much of the infrastructure needed to test embodied AI. Its engineers understand safety zones, cycle times, downtime, spare parts, and returns. The humanoid becomes another layer in an existing automation stack. The supply chain may be China's strongest advantage. A humanoid robot appears futuristic, but its body is assembled from technologies already produced for electric vehicles, drones, smartphones, batteries, machine tools, and industrial automation. It needs electric motors, precision gears, bearings, cameras, force sensors, wiring, processors, cooling systems, and machine structures. China manufactures nearly all of these at deep scale. In Shanghai, officials say nearly 90% of components used by some local embodied robots can be sourced domestically. That figure is often confused with China's share of robot production, but the distinction matters. Local sourcing means shorter lead times, faster redesigns, and lower logistics costs. If a joint, camera, or motor changes, engineers can work with a nearby supplier instead of waiting months for an import. This creates the feedback loop that transformed batteries, solar panels, and electric vehicles. More producers attract more suppliers. Suppliers lower component prices, encouraging larger orders and more experiments. Those orders justify automated lines that improve consistency and reduce cost again. Once the loop accelerates, rivals with fragmented supply chains can struggle even when their prototypes are technically excellent. Company figures show how quickly the market expanded. Unitree said it delivered over 5,500 humanoid robots in 2025 and produced over 6,500. Industry data placed AgiBot near 5,200 shipments, including about 1,300 full-size units. These totals include research, education, entertainment, data collection, and commercial machines, not only factory workers. Even so, they mark a major leap from laboratory-scale output. China's industry ministry said over 140 domestic manufacturers released more than 330 humanoid models in 2025. That competition is both a strength and a warning. It speeds innovation but also creates duplication, exaggerated marketing, and companies that may disappear. The eventual leaders won't be chosen by the most viral video. They will be chosen by reliability, cost, service, software, and repeat orders from real customers. Unitree shows the power of aggressive hardware pricing. Known first for quadruped robots, it moved into humanoids with compact machines that walk, balance, recover, and perform dynamic movements at prices far below older research platforms. That doesn't make them factory-ready, but it broadens the developer base. Universities, startups, and integrators can buy real hardware, collect data, and build applications without enormous budgets. AgiBot is pursuing full-size humanoids, wheeled embodied robots, and machines built for data collection or industrial tasks. Its advantage isn't one body shape, but the attempt to connect hardware with training systems, operational data, and scalable production. Its rapid output shows how quickly a Chinese startup can move when suppliers, factory space, engineering talent, and local support are concentrated in one industrial region. UBTECH has taken a more industrial route with its Walker series, testing robots in automotive and electronics environments. The machines have been used for material handling, inspection, and repetitive operations that fit structured factory workflows. UBTECH began mass production of the Walker S2 and delivered batches numbering in the hundreds, while announcing plans to expand annual capacity. The important word isn't humanoid, it's production. Walker S2 also highlights a problem that every mobile robot must solve: energy. A machine that stops for hours to recharge can't deliver continuous factory value. UBTECH designed the robot to swap its own battery, allowing a fleet to rotate power packs and remain active for longer periods. This is a practical feature, not a theatrical one. It shows the industry shifting attention from how a robot looks to how it survives an actual work schedule. The strongest evidence comes from repetitive factory trials. In one electronics deployment, AgiBot machines completed an 8-hour shift and performed over 2,200 pick-and-place operations while matching the production line. They also identified defective products and communicated with factory systems. One trial doesn't prove universal reliability, but this is the kind of measured task that moves robotics from publicity into procurement. For now, the jobs best suited to humanoids are narrow and repetitive. Moving totes, feeding machines, transferring parts, scanning shelves, sorting packages, inspecting surfaces, and carrying materials between workstations. These tasks consume labor without always requiring advanced judgment. A robot doesn't need to understand an entire factory. It needs to complete one useful sequence safely and repeat it thousands of times. Why use a human-shaped machine when robotic arms and wheeled platforms already exist? The answer is infrastructure. Factories, warehouses, elevators, doors, ladders, tools, and workstations were designed around the human body. A humanoid can potentially enter that environment without forcing the owner to rebuild everything. It can walk to a station, reach a shelf, use 2 hands, and move to another task. That flexibility is the central promise. The humanoid shape isn't always the best solution. Fixed arms are faster and more precise for many assembly operations, while wheeled robots are more efficient on flat floors. Specialized machines can outperform general bodies at lower cost. The market will therefore be mixed. Humanoids will win where mobility, reach, adaptability, and human-compatible tools justify their complexity, not simply because legs look advanced. Hardware is only half the race. A useful humanoid must perceive objects, estimate distance, maintain balance, plan movement, understand instructions, and recover when conditions change. Traditional robots depend on carefully programmed routines. Embodied AI seeks more adaptability by combining vision models, language systems, motion control, and learned policies. That is what lets a robot respond when a box is slightly misplaced. Developers increasingly teach robots through demonstration rather than coding every joint movement by hand. A person performs a task through teleoperation or motion capture, while the system records images, forces, positions, and outcomes. Thousands of examples can train a model to reproduce the behavior. Physical errors still have consequences. but this method can reduce the time needed to move from one task to another. Data may become more valuable than the robot body. Every grasp, failed lift, avoidance maneuver, battery swap, and completed shift can improve future software. A company with thousands of deployed machines collects operational experience faster than a rival with a few prototypes. The result is a flywheel. More robots create more data, better data improves the model, and a stronger model makes the next fleet more useful. China's manufacturing scale gives that flywheel unusual momentum. A laboratory robot sees a controlled environment. A robot deployed across electronics, automotive, logistics, and appliance factories encounters changing light, objects, floors, workflows, and human behavior. Those variations expose weaknesses simulations may miss. Companies able to capture and organize that experience can improve dexterity, navigation, and reliability faster. Simulation remains critical because real-world training is slow and costly. Developers can create virtual factories, generate many movements, and test policies without damaging hardware. The challenge is transferring those skills into reality, where friction, shadows, loose cables, and imperfect objects behave differently. Strong platforms will combine synthetic training, teleoperation, human demonstrations, and learning from deployed fleets. Standardization is another battlefield. China introduced a national framework covering humanoid robots and the embodied intelligence lifecycle. Standards can define interfaces, safety tests, performance measures, data formats, and component compatibility. Without them, each maker creates an isolated system. With them, suppliers can reuse parts, factories can compare machines, and customers can demand measurable results instead of dramatic claims. Moving from prototypes to products also requires lines designed to build the robots. In Hubei, one humanoid assembly line reported hundreds of units in 2025. In Shenzhen, a pilot line can assemble a research robot in about 2 hours, while a Foshan facility is designed for annual capacity above 10,000 units. Capacity isn't the same as sales, but it reveals how seriously the industry is preparing for scale. Shanghai has launched an automated line for integrated humanoid joints, initially designed for 100,000 units a year. Joints are demanding because they combine motors, gearing, sensors, control electronics, and structural strength in a small package. Consistent production is essential. Excellent software cannot save a robot if its joints overheat, wear unevenly, drift out of calibration, or behave differently from unit to unit. These investments target a problem hidden by polished demonstrations: consistency. Building one robot by hand is difficult. Building 10,000 that move the same way is an industrial challenge. Fasteners need correct torque, cables need safe routing, sensors require calibration, batteries need testing, and software versions must be controlled. Mass adoption begins only when robots become repeatable products rather than individual projects. Cost will determine how quickly adoption happens. A factory doesn't compare a robot only with one worker's salary. It calculates purchase price, financing, integration, maintenance, energy, software fees, parts, supervision, downtime, and expected life. It also measures productive hours. A cheap machine that works half the time can cost more than an expensive one that operates reliably across several shifts. The human side is equally complex. Workers require wages, training, protective equipment, scheduling, management, and benefits. But people solve unexpected problems, communicate instantly, switch tasks, and use common sense in ways robots still can't match. The business case is strongest where work is dangerous, exhausting, understaffed, or highly repetitive. Early deployment will therefore be selective rather than universal. Humanoid robots carry costs that headlines ignore. They need technicians, charging or battery infrastructure, secure networks, software updates, safety systems, and replacement components. Factories may redesign workflows even without rebuilding the space. Insurance and liability rules must evolve. Cybersecurity is critical because a compromised machine can move through the real world. Replacing labor is not as simple as adding a robot. Adoption will arrive in stages. Companies start with a controlled task, a limited area, and close supervision. Engineers measure cycle time, error rates, energy use, interventions, and downtime. If the economics work, deployment expands. If the machine fails too often, it is reassigned or removed. Early fleets will look less like independent androids and more like managed industrial equipment connected to a central operating system. The phrase replacing human workers must be used carefully. China hasn't removed people from its factories, and today's humanoids cannot perform most jobs. What is happening is a gradual transfer of specific tasks. A worker who once moved bins for an entire shift may supervise several robots. Another may handle exceptions, maintenance, or quality decisions. Automation changes the structure of work before it eliminates occupations. Labor shortages may accelerate the transition faster than layoffs. Manufacturers struggle to recruit for night shifts, heavy handling, hazardous areas, and monotonous inspection. A robot filling an empty position creates less resistance than one introduced only to cut a workforce. Aging societies in China, Japan, South Korea, and Europe face similar pressure, so demand for physical automation is not limited to one country. New occupations will grow around the machines. Factories will need fleet operators, robot technicians, safety engineers, data annotators, simulation specialists, application designers, maintenance planners, and cybersecurity teams. Some jobs require degrees, but many resemble skilled industrial trades. Timing is the challenge. Workers need training before old tasks disappear, and productivity gains must be shared broadly. Safety could slow everything. A humanoid is heavy, powerful, mobile, and built to work near people. It must detect humans, limit force, avoid falls, stop reliably, and behave predictably when sensors fail. A viral video can hide dozens of unsuccessful attempts. Factories cannot. They need documented failure rates, emergency procedures, certified components, and clear responsibility when a machine causes damage or injury. Reliability matters as much as intelligence. A robot that understands speech but needs frequent resets won't survive industrial procurement. Bearings wear, cables loosen, cameras collect dust, batteries degrade, and software updates introduce errors. Winners will build service networks as carefully as AI models. Customers will ask how quickly a joint can be replaced, how long support lasts, and whether parts will exist in 5 years. China isn't alone in this race. Tesla is developing Optimus around its AI, battery, and manufacturing capabilities. American startups are targeting logistics and industrial work. Japan and South Korea remain leaders in robotics, components, and factory automation. European firms bring deep safety and precision expertise. The competition isn't settled, and the most advanced general-purpose robot may still emerge outside China. China's advantage is different. It may not need the single best prototype if it can produce capable machines faster, cheaper, and in larger numbers. Industrial history shows that manufacturing scale reshapes technology. Products improve when thousands of units reveal defects hidden in laboratories. Suppliers invest when orders become predictable. Volume turns technical progress into an economic system. That system could reshape global trade. Countries may import Chinese humanoids because local alternatives are too expensive or unavailable. Factories could depend on Chinese joints, motors, batteries, controllers, and software even when the final robot carries another brand. Governments would then face familiar questions: price versus security, openness versus strategic dependence, and efficiency versus control of critical infrastructure. The headline figure, 84% of global shipments in 2025, needs context. The market was still small, definitions vary, and many units went to education, research, entertainment, exhibitions, or data collection rather than industrial labor. Early leadership can fade as a market matures, yet a share that large gives Chinese firms experience, revenue, supplier leverage, and a rapidly expanding installed base. The next phase will be harder. Walking demonstrations and small batches attract attention, but customers will demand measurable productivity. Robots must work longer, learn faster, use less power, handle more objects, and require fewer interventions. Prices must fall without sacrificing quality. Companies must prove that their machines deliver returns over years, not only during stage trials or controlled showcases. Factories won't be the final destination. As reliability improves, similar bodies could enter warehouses, retail stores, hospitals, power facilities, construction sites, and elder care. Each environment creates new technical and regulatory problems. Warehouses are structured, hospitals are crowded and sensitive, and homes are unpredictable. The path to a general assistant will be gradual, with specialized uses arriving first. The deeper contest is over the operating system for physical AI. The company controlling the robot body may not capture the most value. Software models, developer tools, cloud training, data platforms, standards, maintenance networks, and application markets could matter more. China is trying to build all of them together. That full-stack approach matters beyond the number of machines shipped in 1 year. For manufacturers, the message is clear. Humanoid robots are no longer a distant concept that can be ignored until the next decade. They are entering evaluation now. Companies must identify suitable tasks, prepare data, redesign workflows, train staff, and understand safety rules before rivals gain years of experience. The first advantage may not come from owning the most robots, but from learning how to use them. For workers, the future is neither a simple disaster nor an automatic promise of easier jobs. Some repetitive roles will shrink, while technical roles will appear. Productivity could raise wages and reduce dangerous labor, or concentrate benefits while increasing insecurity. Policy, training, and corporate decisions will determine the outcome. The social system around the machines will decide whether automation becomes broadly beneficial. China hasn't replaced the human workforce. What it has done is build the largest early platform for testing whether humanoid robots can become a real industrial product. With most 2025 shipments, over 140 manufacturers, hundreds of models, dense local sourcing, and new production lines, the country has created momentum that competitors can't dismiss. The robotics race has moved from isolated prototypes to manufacturing scale. The final question isn't whether a robot can dance, run, or lift a box during a demonstration. It's whether millions of machines can be built consistently, deployed safely, maintained cheaply, and trained to perform useful work. China believes its supply chains and factory system can answer that question faster than anyone else. If it succeeds, the next great export may not be a phone, battery, or electric car. It may be a programmable worker. Artificial intelligence spent the last decade learning to write, see, speak, and reason inside computers. Humanoid robotics is the attempt to connect those abilities to the physical economy. That transition will be slower and messier than the headlines suggest, but it has already begun. The country that combines capable AI with reliable mass manufacturing will shape how factories operate, how supply chains compete, and how human labor changes. If you enjoyed this deep dive, subscribe and share your view in the comments. Will humanoid robots mainly fill dangerous and unwanted jobs? Or will they displace workers faster than economies can adapt? And can companies outside China match the speed of a supply chain that's already moving from thousands of units toward true industrial scale? The machines are arriving, but the rules of the new workforce are still being written.